Hello, good morning. Mela, bonġu. Mela, illum l-aħħar lezzjoni qabel il-holidays. Mela. Kemm qegħdin ftit. Alright, ħanibda tamma. Ħanibda. Alright, mela. Illum li ħanamlu ħanibdew diġà bdejna xi ħaġa żgħira fuq it-topic li jmiss, imma ovvjament illum ħanibdew kif suppost. Mela, ħanaraw daqsxejn x'għadna l-bieraħ. Mela, yesterday we were talking about forces because we're going to use forces in Newton's laws. Newton's laws is all about how the forces interact in a way to make an object move at constant velocity or to move in acceleration. All right? And we said that the forces can be subdivided into two groups, the forces which are inside the atom and outside the atom. We're going to talk about forces outside the atom because we're going to investigate situations macroscopically, so from outside. And we also said that these forces can be subdivided into two groups, gravitational and electromagnetic. All forces outside the atom can be arranged in these two groups, gravitational or electromagnetic. Now, today, in fact, we're going to talk about these types of forces. We're going to mention the most important forces, all right, the most important forces, and I'm going to get into detail of the most important forces. In the topic, in your notes, Newton's laws of motion, on page, from page 56 to page 57, from page 46, from page 46 to page 57, from page 46 to page 57, you have an appendix where you have very detailed descriptions, very detailed discussions about each type of force that we're going to use throughout the topic. All right, throughout the topic. Therefore, I'm going to mention the forces, I'm going to mention the most important things about these forces, but if you need more detail about those forces, you can find that in the appendix. All right, when you have an appendix with a topic, in the appendix I will put information which is a little bit more than you are required in the syllabus, but you will need that information to understand thoroughly that concept. So, the first page in Newton's laws is about the different types of forces. We already talked about this. Therefore, now we're going to start talking about the different types of forces. So, it's very important that you keep in mind a checklist of forces. Why? Because in Newton's laws, you're going to be presented with a situation, and you have to draw the forces on that object. If you leave any important forces out of the diagram, if you don't draw them, obviously that will affect the rest of the problem. Therefore, it's important to keep a checklist in your mind of forces to check if those forces are acting on the object or not. And that's what I'm going to do right now. So the force, and the first and most important force that you have to keep in mind is the weight. All right, now obviously most of those forces that I'm going to write today, that I'm going to discuss today, you already know those forces, all right, but we're going to get a little bit deeper, a little bit in more detail for each and every one. The weight is another way how to say force due to gravity or gravitational force or gravitational pull. Daw kollha jfissru l-istess. It's very important that when you have the weight or the force due to gravity, you don't name it gravity. Kultant jagħtiwkom apposta domanda vera sempliċi. Alright? Biex jiċċekkjaw jekk intom x'tagħmlu dal-iżbal għax nafu dan huwa żball komuni ħafna. Ħafna studenti jgħidu il-gravity. Alright? Attenti, that's not gravity. Gravity is the concept, is the field. Alright? You have to say force due to gravity. Alright? Or gravitational force or weight. The three of them are the same thing. To calculate the weight, it's very easy. It's the mass times g, where g is the acceleration to the gravity, 9.81 meters per second squared. We have already started using it. Alright? So, pay attention, this is something from O level. Weight and mass for physics are completely different. Mass is in kilograms, weight is the force due to gravity. So, if you have an object, the weight is always going to be drawn exactly from the center of the object and always downwards. Whatever the orientation of the object, whatever on whatever the object is resting, it doesn't make any difference. The weight is always drawn vertically downwards, because in this topic we're going to concentrate only on objects which are on the surface of the earth. Therefore, the weight is always downwards. Then we have a topic later on, where we're going to talk about gravitation. And then when we're going to talk about gravitation, we're going to talk about even an object which is very far away from the Earth, for example, or it's at different positions around the Earth. In that case, since we're going to widen our view, then you can have the gravity which is at different directions, alright? But in this topic, the weight is always pointing downwards, okay? I'm going to talk more about the weight in the future, in the future topic, in the future lectures, alright? Imma mhux se nsemmihom għalissa. Imma iktar qudiem ħansemmi daqsxejn iktar fid-dettall u nitkellem daqsxejn iktar fid-dettall fuq il-weight ukoll. So, that's the first force. Now, in the same group with the weight, there is another force which is very, very important. Attenti, għax dan kultant insewh. Which is the reaction or contact force. The reaction or contact force. The reaction or contact force is the force when an object is in contact with another solid object. Attenti, għax the reaction force flow level ma nafx għaliex. Ittu ftit il-ġemp. Ma tatux daqshekk kasa. The reaction force is one of the most important forces that we have in the universe. Ħantikom din l-idea biss u ħalli tifhmu. We manage to walk, a car manages to move forward, a boat manages to move forward, a rocket manages to move, because there is a reaction force. Li kieku ma teżistix reaction force, kieku l-oġġetti ma jimxux il-qoddim. Kull oġġett li jimxu l-qoddim, li għandu xi tip ta' engine biex jimxu l-qoddim, jimxu l-qoddim għax hemm xi tip ta' reaction force. Reaction force mela tiġi, if you are pushing an object, the object will push you back. Alright? L-idea sempliċi biex tifhmuha di. When you are leaning with the wall, alright, you already have a reaction force. Għaliex? Because if you are pushing the wall and the wall is not pushing you back, you will pass through the wall. Taqblu mija jew le? Dik waħda. It-tieni ħaġa. If you are leaning against the wall and you push the wall using your hands, you will be pushed forward, ux vera, taqblu miegħi. Dak huwa l-mod infatti kif aħna jirnexxielna mmexxu l-affarijiet il qudiem. Hekk jirnexxilhom jimxu l-affarijiet il qudiem billi nimbuttaw oġġett u l-oġġett jimbuttana l qudiem. Għaliex? Għax hemm idea u dal-konċett importanti ddaħlu f'idejkom, f'moħħkom. Inti ma tistax tagħmel fors fuqek innifsek li tiġbdek il qudiem. Tista' tiġbed lilek innifsek il qudiem? Ma tistax, aħsbu ftit. Ma tistax tapplika force fuqek innifsek biex inti timxi l-qoddim. Mela biex aħna nimxu l-qoddim, irridu nimbuttaw xi ħaġa u dik l-oġġett jimbuttana l-qoddim. U għalhekk ir-reaction force tiġi importanti. So, how are we going to draw the reaction force? Therefore, if you have the ground, for example, and you have an object, so the forces on the object are the weight directly downwards. The reaction force is always drawn between the surfaces which are touching each other. Mela nibdew in between the surfaces which are touching each other. And the reaction force is always acting on the object which is touching the other object. Ġifieri, jekk inti jien qed nikkonċentra fuq il-box, if I'm drawing the forces on the box, the reaction should always act on the box. Alright? So the box is pushing the ground. This is the reaction of the ground on the box. So the reaction force is acting on the box, will affect the box. Issa. The reaction force is always drawn 90 degrees to the surfaces which are touching each other. Ġifieri jekk għandek the surfaces are touching each other like that, the reaction force is going to be perpendicular. If they are touching each other like that, the reaction force is going to be perpendicular again. So if I have an inclined plane, the weight is always drawn directly downwards, but the reaction force will be drawn perpendicular to the surfaces which are touching each other. The box is pushing the inclined plane, so the inclined plane will push the box back. Issa, a misconception from our level, u din misconception attenti għalija. The reaction is not always equal to the weight. Alright? It's not always equal to the weight. Sometimes it is equal to the weight, but it's not always equal to the weight. In fact, the reaction force and the weight are not a Newton third law pair. Edin tifmuni. Għax għamiltu flow level bekket insemmija, tafu xinu Newton's third law, ġvera. Il-weight u reaction mumiex Newton third law pair, għax biex ikollok Newton third law tgħidlek the force is always equal and opposite. Imma reaction u weight mumiex always equal and opposite, ġveri dawn mumiex ta' Newton third law, mumiex l'action u reaction, il-weight u reaction. Attenti. U għantikom eżempju. If you are jumping from a high object, alright, and you are landing on the ground, okay? When you land on the ground, as soon as you touch the ground, the weight is always the same. Dik ma tinbidilx, għax il-weight hija l-force due to gravity. But the force that you feel on your feet, alright? Ġifieri hija the push of the ground on your feet. Is it the same, larger or smaller when you are just standing? Isa, as soon as you land, when you jump from a high object. Larger. Therefore, the reaction force, that's the reaction force. In that case, the reaction force is larger than the weight. Because you feel a force on your feet of the ground pushing you upwards, which is larger than your weight. And it's important that the reaction in this case is larger than your weight, because in this manner, you will have a resultant force on yourself upwards, and that resultant force is actually the force which will decelerate you. Alright? Which will decelerate you. Ġifieri, the reaction force is not always equal to the weight. Another thing about the reaction force, which is very important. The perception of our weight comes from the reaction force as well. Xi tfisser? The perception of our weight, how heavy we feel ourselves, we feel our weight not according to our weight. Għaliex? Because our weight is actually, it's the gravity which is pushing us down. But actually, the force that we feel on our feet is the reaction force. Għodu waħsbu ftit. When you are standing, what you feel, the weight of yourself, actually you feel heavy according to how much the ground is pushing you upwards. It's the force that you feel on your feet and on the muscles of your legs, which is actually the reaction of the ground on yourself. So we perceive our weight, we feel heavy or light according to the magnitude of the reaction. If the Ajdli, Suzanne. Yeah, bizballo, right. So if the reaction is larger than the weight, you will feel heavier. If the reaction is smaller than the weight, you will feel lighter. Ħantikom eżempju fejn tiġrilkom di. Meta tkunu ġo lift and you push the button to go to a lower floor. As soon as the lift accelerates downwards, you feel uplifted, vera? Għad ħassejtuh dak il-feeling. Tossukom jiskom tinqataw ftit minn ġewwa. Għad ħassejtuh, jew jien biss inħossom dawn affarijiet. You feel a little bit uplifted. Ġifieri, you feel a little bit lighter than usual. It's not because you're lighter than usual, it's because the reaction on your feet is a little bit smaller than the weight. Therefore, you will feel lighter. Alright? On the other hand, in the opposite way, if you are on a lift and you push the lift to move to a higher floor, as soon as it accelerates upwards, you feel as if you are being smashed. تحسه hisek titaffeċ ftit. Alright? Therefore you feel heavier. That is because the reaction on your feet is larger than the weight at that moment. Therefore we perceive our weight according to our reaction force. The extremity of this effect is on astronauts. When you have astronauts in the International Space Station, ġilli rajtu għam l-astronauti jifloat jaw, and we say there's no gravity, ux vera. Dik hija kompletament ħażina. Attenti. L-astronauti, meta jkunu għedin fl-spaceship tagħhom li hija l-International Space Station ħafna drabi, they are orbiting very, very close to the Earth. They are practically just outside the atmosphere. Fatt ikun ma jkunu huma just 500 kilometers. They are very, very, very close to the Earth. The acceleration due to gravity on the astronauts in the International Space Station is just a little bit smaller than 9.81, forsi hija 9.6 jew 9.7 xi ħaġa hekk. Alright? Therefore there is a weight, but they feel weightless. Why they feel weightless? And actually they can float in the spaceship. Why? Because the reaction, how much do you think is the reaction? Since they are feeling weightless. Kemm taħsbu li hija reaction fuqhom l-astronauti hemmhekk? Iktar minn minimum, x'tiġi? Zero. The reaction is zero. In fact, they can float. Għaliex they can float? Because they don't need to touch the ground. Because they don't have a reaction on themselves. Għalhekk iħossuhom weightless. Because there's no reaction. Issa l-question mark hija l-kbira. Kif jista' jkun ma jmissux mal-art? Alright? Kif jista' jkun reaction hija zero? Imma dik mhux se nirrispondi issa, mbagħad nirrispondu aktar quddiem. Imma l-astronauti jħossuhom weightless because the reaction on their body is zero. Therefore, actually they don't need physically to touch the ground. They don't need physically to touch the ground because there's no reaction force. The ground is not pushing them. Alright? Sawnek alright? Sissa, bejbetu ieħor. L-aħħar żewġ affarijiet fuq ir-reaction force. Qed nieħu ftit ħin fuq ir-reaction force għax ir-reaction force hija importanti ħafna ta' ħafna importanti, ħan nintaqgħu ħafna magħha. The symbol of the reaction force instead of R, we can also give it the symbol of capital N. Why capital N? Because sometimes the reaction force is also called the normal reaction force. Normal in physics or in mathematics, normal means perpendicular. Since this reaction force is perpendicular to the surfaces which are touching each other, we can call it normal reaction force. And sometimes instead of R, it is given the letter N. So we can give it either R or N. Both of them are correct. Sawnek kollu sew. One last thing about the reaction force. So the reaction force is the force exerted by an object which you are pushing, and the object is pushing you back. Now, therefore, if you are touching 3 objects, you have 3 reaction force on you. If you are touching 4 objects, you have 4 reaction force on you. In your case, right now, you are all sitting down. In your case, at least, there are 3 reaction force on your body. Why? Because you are touching the back of your chair, so the back of your chair is pushing you back, or else you will pass through the back of your chair. Kiekum hemm xi reaction force b'għaddej. Alright? You are sitting on your chair, alright? So the horizontal part of the chair is pushing you upwards, and you are touching the ground with your feet. Therefore, the ground is pushing your feet upwards. Therefore, at least you have 3 reaction forces. If you are resting your arms on your desk, you have a 4th reaction force because you're touching the desk as well. Therefore, when drawing an object, when drawing the forces, when you have to draw the reaction forces, you have to ask yourself, with how many objects is the object touching? And you have to draw the reaction forces according to the objects that you have. So, for example, if I have this situation, I have 2 books resting on a table. And I have to draw the forces, first on A and then on B. Let's start on A. The forces on A are the weight and A is touching what? Isa. B. So A is pushing B, then B is going to push A, and that is the reaction of B on A. So this force is affecting A, all right, because it's on A. If I redraw the diagram, and now I'm going to draw the forces on B. Now I'm going to draw the forces on B. So I have the weight of B. B is touching how many objects? 2. It's touching A and it's touching the table. So B is pushing the table down. So the table will push B upwards. So I have that one, which is the reaction of the table on B. So it's affecting B. But then B is touching A, so A will push B. And A will push B in what the direction? Downwards. Therefore, we have the reaction of A on B. That's the reaction of A on B. So there are two reactions acting on B. In fact, if A is heavier, all right, it will push more B and B will get smashed between these two reaction forces. All right. Now, another important thing to notice here is that I didn't draw the forces on both objects at the same time at Tarawni. First, I drew the forces on A only. Then I drew the forces on B only. In Newton's laws, this is a very, very important skill to master. You can't draw the forces on more than one object at the same time. If you do that, you will start cancelling out forces and you will not understand the system. When you are drawing forces, you have to draw the forces on just one object at a time. On just one object at a time. The last thing about reaction forces, the Newton third law pair, now you can see the Newton third law pair. Look, this force is the reaction of B on A. This is the reaction of A on B. Are you seeing them? Those are a Newton's third law pair. Dawn huma action u reaction. Alright? Dawk huma. Alright? Ġifieri, issa kif ħanaraw aktar qudiem fi Newton's third law ħani qafaw għax issa ħan niddiskutu aktar qudiem. Imma in Newton's third law, the two forces of Newton's third law cannot be acting on the same object. Never. Alright? Because it's the effect that an object affects one object, therefore the other object will affect the other object. So the forces are always one on one object and the other one on the other object. So the weight and the reaction are never Newton's third law pair. Reaction forces have a Newton third law pair as a reaction force as well. Umbagħad dik ma niddiskutu aktar qudiem. So that's about reaction forces. Attenti għax reaction forces, they are very, very, very important. Alright? Reaction forces is also a dynamic force, so it changes its magnitude according to the situation. Alright? Ġifieri tinbidel skont is-sitwazzjoni. Kif qed taraw ġieli tkun daqs il-wej, ġieli le, etc. Għajdli.
You said that the reaction force is opposite to the weight or the gravitational force.
Stenna, le, jekk għattek għatta mela. Normally it is like that. Normally it is like that. Why? Because if the earth is pushing the object downwards, is pulling the object downwards, then in a natural way the object will push the ground downwards. Therefore the ground will have to push the object upwards. So in most cases the weight is downwards and the reaction is upwards. But for example in this case, it's not exactly the same case, vera. The weight is downwards, but since the object is pushing the plane and the plane is at an angle, the reaction is in that direction. Fimna? Ġifieri le, jekk għatta hekk ma tix tajba, hija b'mod l-iktar li nintaqgħu magħha li l-weight tkun li s reaction tkun fuq. Le, reaction tkun skont kif qed timbotta l-oġġett. Infatti, sistema għax insejt insemmijilkom li nintaqgħu ħafna magħha hija din. If you have a ladder or an object which is resting on the ground and against the wall, so we have the weight. And then there are two reactions because the ladder is touching the ground, so it's pushing the ground downwards, therefore the ground will push the ladder upwards. So that's the That's the reaction of ground on leather. And then there's another reaction because the leather is pushing the wall, so the wall will push the leather to the left. So that is the reaction of the wall on leather. As you can see, both forces are acting on the leather, alright? But in that case, therefore it's pushing the ground, so the ground will push back. It's pushing the wall, so the wall will push back, alright? طيب. Now, what happens if the object is not touching another solid object, but it's touching something else? So, what happens if the object is immersed or partially immersed in a fluid? In this case, you have another type of force, which is called the upthrust. The upthrust is the force, is the opposing force when immersed in a fluid. So this is the opposing force when touching an object. When touching. This is the opposing force when immersed in a fluid. When immersed in a fluid. When we use the word fluid in physics, means a gas or a liquid. So whenever you have an object which is immersed in a fluid, it can be immersed in air, it can be immersed in water, in oil, alright? So in a fluid, you don't have the reaction force because the object is not pressing, it's not pushing a solid object and the solid object will push back, alright? But it is still acting against the particles of the fluid. And therefore the particles of the fluid will push back the object, and therefore it will push back the object using the upthrust. So this object will have the weight, and in this case you will have the upthrust. It's called the upthrust because it's always pointing upwards. Upthrust is always pointing upwards, always. Alright? So when you have an object which is immersed in a fluid or partially immersed in a fluid, partially immersed ġifri bħal mija boat per eżempju, in that case you will still have an upthrust. The upthrust decides if an object floats or sinks, alright? Or else if it moves upwards in the fluid. Ġifiri l-upthrust tidħol ħafna f'din l-idea ta' floating, sinking, etc. I'm not going to get more in detail about upthrust because we're going to discuss upthrust in more detail in the next lectures. Actually, you need to know how to calculate the upthrust. The person who discovered how to calculate upthrust was Aristotle. Ġifieri l-upthrust ilna nafu kif naħdmuha u kif nużawha minn żmien il-Griegi, ilna pratikament 1000 sena. Alright? Jew ftit iktar minn 1000 sena. Nafu kif nikkalkulaw l-upthrust. Now, what you have to pay attention about the upthrust is that sometimes the upthrust is practically negligible. Alright? It's practically negligible. When the fluid has a very, very, very low density, as for example is air, alright? When it has a very low density, the upthrust is so small that sometimes it can be considered as negligible. For example, all of you are immersed in air. But the upthrust that there is on you, so you have an upthrust, alright, acting on you, but it is so small that it's practically negligible. In fact, we never draw the upthrust acting on a person who's standing in air, or on a building which is standing on air, or on an aeroplane. We don't draw the upthrust. But then in other situations, for example, a hot air balloon, tafu xinu hot air balloon? Ux vera. The upthrust in that case is very important. It's the upthrust which drives the hot air balloon upwards, alright? Or which controls the hot air balloon to go downwards. A balloon filled with helium, again, the upthrust is very important. It's the upthrust which makes the helium balloon move upwards. Ġifieri, di tkun daqsxejn problema fl-upthrust. Issa, meta naraw il-formula tal-upthrust suppost għandha tgħinkom, kultant iridu nagħtu kasa u kultant le. Alright? Li hu żgur huwa that when an object is immersed in any fluid, the upthrust is very important. Dik dejjem. liquid, sorry, in any liquid, water or oil or something like that, meta jkun liquid l-aktar dejjem tridu tagħtu kasa, dejjem. Meta jkun fl-arja toqgħod attent skont is-sitwazzjoni. Issa aktar quddiem nitkellmu. So, this was the first group of forces. So we have the weight. If it's touching a solid object, you have the reaction. If it's immersed in a fluid, you have the upthrust. Dak l-ewwel group. Alright? Now, the second group of forces. The second group of forces comes when you have objects which are sliding against each other. So if you have an object and this object is moving on the ground, alright, then there is a force because you have two surfaces which are sliding against each other. What's this called when you have two surfaces sliding against each other? Friction. Friction is the opposing force to sliding. Alright? Therefore, if you have two objects which are sliding, the frictional force is always drawn in the opposite direction to the direction of motion and parallel to the surfaces. So not perpendicular as the reaction now, parallel. So if the object is moving in that direction, the friction should be pointing in the opposite direction. So it has to be drawn. It has to be drawn parallel to the surfaces and in the opposite direction. That is the friction. Alright, that's the friction. Now, the friction is another dynamic force. It's a force which changes its magnitude according to the situation. Alright? And moreover, the friction is not always present when you have actual sliding, when the objects are actually sliding. Even if the objects, there is the possibility that they can slide, you will also have a frictional force acting on it. Let's take this example. For example, if I have an inclined plane and I have an object, the object has the weight acting on it, vera, and the reaction force which is acting perpendicular. If the object is on the plane and it's not moving downwards, remember there's a component of the weight which is pulling the object downwards, therefore it should be accelerating downwards. If it's not moving downwards, it's just on the slope, it means that there is the friction which is keeping the object from moving. So you can have a friction when the object is not moving. So if there is the possibility of sliding, in fact, this object can slide downwards, there's the possibility that this object slides downwards. So, since there's the possibility that this slides downwards, therefore there must be a friction pointing in the opposite direction to that possible sliding. Therefore, there I have a friction acting against the object, although the object is still not moving. So the friction is not always there when the object is moving. If there is the possibility of sliding, you will have a friction as well. Alright? Sawnek qegħdin nifhmu jew le? Sawnek qegħdin nifhmu. Issa, I said that the friction is a dynamic force, so it changes magnitude according to the situation. So let's take this example. For example, this is a situation from real life. I think that at some time or another you had this experience. Let's say you have a wardrobe which is full of objects and you have to move it, so it's very heavy. Alright? And you are going to try to push this wardrobe. So you are applying a force. Let's say you are applying a 10 Newton force on the wardrobe. If the wardrobe is heavy, will the wardrobe move immediately as soon as you apply the force? No. Why? Because you're trying to slide it, but a force is opposing you. And that force is practically the frictional force. Alright? So it's still not moving. But since there's the possibility of moving because you're pushing it, alright, then you will have a frictional force acting against you. And that frictional force, if that frictional force is exactly 10 newtons, then the wardrobe will not move. And Sawnek, alright? Sawnek, okay? But if you increase the force 15 newtons, the frictional force, being a dynamic force, it's a force which can change according to the situation, will increase 50 newtons as well, so the wardrobe will still not move. But then at a certain point, if you continue on increasing that force, for example, enough 30 newtons, there's a limit for the friction. Iġifieri il-friction għandha limitu li ma tistax taqbżu iktar, mela jien ngħidu 30 newtons all right, telat 30 newtons, but then as soon as you change the force to 35 newtons, the limit of the friction was 30 newtons. Mela l-ikbar friction li jista' jkollok between these two surfaces is 30 newtons. So what happens is, if you exceed the limit of the friction, then you will succeed to move the wardrobe, and that's actually what happens. So ġvera, jekk tibqa' żżid il-force, jekk inti ma tkunx tista' jiġi xi ħadd jgħinek, at a certain point the wardrobe will move. The wardrobe moves when the force that you are applying is larger than the maximum friction that you can have. The maximum friction that you can have is called the limiting friction. It's called the limiting friction. And the limiting friction has a formula. So we can actually calculate the limiting friction, the maximum friction that you can have between two surfaces. Issa. The limiting friction formula is not in the syllabus. So you're not going to find the limiting friction formula in the data booklet, but you can be given the formula in the problem to use it. U rajta ħafna drabi di, għalhekk qed insemmija il-limiting friction u ħansemmilkom il-formula, għaliex ħafna drabi jaqbad jitilkom fil-problem u tkunu tridu tużawha. It's not a difficult xejdula formula to use. Alright? It's not a difficult formula. The formula for limiting friction is mu naught n. The formula for limiting friction is mu naught n, where mu naught is called the coefficient of friction. The coefficient of friction depends on the surfaces which are sliding against each other. Therefore, if you have two smooth surfaces, the coefficient of friction will be very small. If you have two rough surfaces, għadin tifhmuni, u rough xiġifieri, if you have two rough surfaces, if you check them under the microscope, they will actually interlock with each other. Alright? They will interlock with each other. So if you have rough surfaces, the coefficient of friction is larger. Even the chemistry of the surfaces makes an effect, because when you have friction, if you go microscopically, jattilkom semmu nitru ħafna microscopically f'dan it-topic, but if we go microscopically, we try to understand what's happening between the atoms of one surface and the atoms of the other, there's a certain type of attractive force between them. So if the chemistry of those surfaces is such that this attractive force is larger, then you will have a larger coefficient of friction. Din isfruttawa fil-Formula 1 fil-tires. Alright? Jekk toqgħodu minnaw dilettant tal-Formula 1 jaf aktar minni, għax minix dilettant ħafna, li ir-roti ibidluhom anki skont ix-xita, alright, u jbidluhom hemm ħafna grades ta' roti differenti. Għaliex? Għax ir-rota tal-karozzi fil-Formula 1, anka tal-karozzi tagħna, maħna ma noqgħodux inbidluhom. Ir-roti tal-Formula 1 li jiġriju bisħana għax bil-friction li tibda tesperjenza r-rota tisħon, ir-rubber jisħon u il-chemistry tar-rubber jibda pratikament jeħel mat-tarmak fil-versions tal-kelma. Il-rubber jibda jdub u jibda jeħel mat-tarmak. Ara meta jkunu ikun hemm dry conditions, jużaw tires apposta li prattikament idubu biex jaqbdu iktar mat-tarmak ħalli jżidu l-friction. Alright, issa aktar qudiem infhemkom il-għala meta jkollok rota aktar ma jkollok friction iktar aħjar. Alright? Biex idubu biex jeħlu iktar. Meta mbagħad tkun ix-xita ma jistgħux jużaw l-istess tip ta' rubber, u mbagħad iridu jużaw rubber li hu iktar qiebes, u mbagħad ir-roti tax-xita jkollhom il-grooves bħalma jkollhom ir-roti tal-karozzi tagħna l-grooves għaliex biex l-ilma tax-xita jidħol fil-grooves u joħroġ jitlaq fuq wara. Għaliex l-ilma in between it-tire u l-ground dak x'jagħmel il-mu naught dan iwaqqaħħulek totali. Allura mbagħad titlef il-friction kompletament. Għalhekk it-tires tax-xita jrid ikollhom il-grooves. Il-grooves qegħdin hemm mhux għall-grip, dik hija konsept ħażin. Il-grooves qegħdin hemm biex l-ilma meta r-rota tafas mal-art, l-ilma jiġi jidħol ġol grooves flok jibqa' bejn it-tajjer u bejn il-ground, u mbagħad meta r-rota ddur l-ilma jintrema fuq wara. Jekk tkunu xi darba wara xi trak fix-xita tindunaw kemm jintfa' kemm l-ilma joħroġ mill-grooves sa wara. Alright? Ġifieri dawn l-affarijiet kollha ġejjin minn hawnhekk. Issa, what is N? Because it's very important N, kif qed taraw hawnhekk. N is the normal reaction force. Is the normal reaction force. Why does the friction depend so much on the reaction force? The larger the reaction force means that the larger the ground is pushing the object. So, it means that the object is pushing the ground with a larger force. The more the object pushes the ground with a larger force, so the more there is contact, the more you have friction. The less the object is pushing the ground, the less there is friction. Therefore, the friction depends directly on the reaction force. Alright? Iktar ma jkolli reaction force kbira, iktar ħajkolli friction. One last thing about friction. Since you can have friction when the object is at rest and when the object is moving, actually there are two types of limiting friction. There is the static limiting friction and the dynamic limiting friction. So there are two limiting frictions. There is the limiting friction when the object is still not moving. And then there is a limiting friction. So the maximum friction varies when the object is not moving and when the same object is moving. In fact, the limiting friction for the dynamic friction, so when the object is moving, is actually smaller than for the static. That's why when you are trying to move the wardrobe, at the beginning it's very difficult to start moving it because the limiting friction of the static friction is very large. So you have to exceed that friction to start moving. But then as soon as it starts moving, it gets much easier, vera? Kif jibda jitċaqlaq l-oġġett u mbagħad huwa vera faċli biex tmexxih. Why? Because then the maximum friction while it is moving it's smaller. Alright? Allura huwa aktar faċli biex taqbes il-friction u tmexxiha waqt li hija mixja milli waqt li għadha wieqfa. Hemm żewġ frictions differenti, limiting frictions differenti. Okay, so hawnhekk. The other type of friction is the drag force mbagħad. The drag force is the opposition when sliding in a fluid. So when you are moving, if you have a ball, for example, and you're moving in air, actually the ball is not sliding against a solid object, but it's sliding against the particles of the air. The particles of the air or the particles of water or of oil, they are actually sliding against the object. So the object will experience a drag force, which is always drawn opposing the direction of motion of the object, alright, as the friction. I'm going to talk about drag force in detail about drag forces more in the future because there are different types of drag forces as well, alright? But the force acting on an object when passing through a fluid is called the drag force. The air resistance is one type of a drag force. Ġifieri meta nuża drag, you can use the word drag instead of air resistance, alright? It's the same thing, okay? Air resistance is the drag force in air, alright? Air resistance is the drag force in air. Nużaw ħafna drag force when we have ships moving through water, because when you're moving through water you have a lot of drag force acting against you, alright? Infatti fl-ilma id-drag force hija importanti ħafna. So friction and drag, these are the opposing forces then to motion, alright? Opposing forces to motion. Mela l-ewwel ftit ma kellhomx jaqsmu ma' motion, weight, reaction and upthrust, alright? Just ħabba contact, etc. Da għandhom xaqsmu ma' motion. So when an object is moving or there is the capability of movement, għandek il-friction, in a fluid għandek il-drag. Okay, l-aħħar żewġ forces huma għalihom imma nużawhom ħafna. Then we have tension. Tension is the force opposing the formation, the force exerted by an elastic material opposing extension jew aħjar deformation. Mela, xi tfisser din? So, when you have an object which is touching, naf li sar il-ħin, imma ħan nipprova l-estija din. When you have an object which is elastic, so it can be extended, and it is being pulled from both sides, jekk napplika force fuq dal-oġġett from one side, it will just move into that side. So we have to pull the objects from both sides. Alright? Issa, when pulling an object from both sides, ma jfissirx that you have to grab the object from both sides and pull it. Alright? If you have this situation, for example, so the box is pulling down the rope, but since it's connected to the ceiling will automatically pull the rope from the other side. Ġifieri mhux bil-fors tkun qed tiġbdu inti, anke jekk l-oġġett qiegħed imqabbad ir-rope qiegħed imqabbad min-naħa u jien ħaniġbed min-naħa, il-ħajt jispiċċa jiġbdu min-naħa l-oħra. So when a rope is two forces are applied and they are stretching the rope, what happens is that microscopically the atoms inside the rope are getting further apart. When they get further apart, the force between those atoms, obviously there are interatomic forces, because the interatomic forces is what keep the rope to remain solid, alright, because the atoms are pegged. If you try to move the atoms apart, the force between them increases. Isek għandek molla bej l-atoms, alright? Jek tipprova tiġbidhom jiġbdu iktar lura. The addition of all those forces between those atoms to try to keep the object in its original length is actually seen from outside as the tension. The tension force, therefore, is always drawn from the ends of the rope or elastic band or whatever, alright, towards the center when you are trying to extend it. Therefore, the tension is the force of the rope on object, attenti, of the rope on object. Ġifiri, il-tension mhijiex force fil-ġol, mhux qed taffettwa l-rope u l-elastic band, hija l-force li il-rope jiġbed lill-oġġett. Alright? Bħal meta tkun fit-tug of war u qed iżżomm il-ħabel fidejk, hija dik il-force li tħoss il-ħabel jiġbed lilek. Dik hija it-tension li aħna nużaw. Alright? So the tension is always drawn from the ends towards the middle point, and it affects the objects which are connected at the ends. Ġifieri, ħafna drabi aħna nużaw waħda mit-tensions biss, għax jekk inti qed tikkonċentra fuq dal-oġġett, by the way aħna qatt ma nikkonċentraw fuq ir-rope innifsu f'Newton's laws, jekk inti qed tikkonċentra fuq dal-oġġett, inti dit-tension biss għandek bżonn. Għax l-oħra qed taffettwa l-oġġett ieħor li qed imqabbad man-naħa l-oħra. Similar to the tension, then there is the compression force li hija ħafna simili għax hija fuq l-istess kunċett. When you have an object and this object is being compressed, the force which is trying to oppose this compression, alright, jiġi hekk, okay, that's called then the compression force. Il-compression or tension force, they are very similar because they are also calculated using the same formula. L-aħħar force ħankun għalaqtom, l-aħħar force ħan intaqgħu magħha hija l-engine force or engine thrust. Whenever we have an engine force or whenever we have an engine thrust, it's the same thing. So whenever you have an object which has an engine, meta ngħid engine, tista' tkun car engine, jista' jkun electric motor, jista' jkun rocket. So whenever you have an engine, alright, on that object there is the forward engine force. The engine force is practically trying to move the object forward. Alright? U aħna we just draw a force pointing forward on the object. Mela kull meta jkun hemm engine dejjem ħanamlu l-engine force. Nixtieq nitkellem iktar fuq l-engine force fid-dettall, imissa nħalli għal iktar il-qudiem. Alright? Għax sar il-ħin u spiċċanna l-ħin. Mela, kemm nerġa' niġborhom malajr. Therefore, the first group, weight, reaction, upthrust. Second group, friction or drag. The last group, which are forces which we're going to encounter a lot, tension. So if you have an elastic object, an elastic band, a rope, or even just a beam or something like that, which is attached, which can extend itself or can compress itself, you have the tension or compression. And finally, if you have an engine on the object, you have the engine thrust or engine force. Alright? Pointing directly forward. Tajjeb, ħani qafaw, happy holidays, moħkom hemm għamlu dak l-imbierek assignment tinsewx tħalluħx għall-aħħar. Tħalluħx għall-aħħar. Jekk ikolkom problema batuli, alright? Ovvjament jekk indum ftit biex nirrispondikom. Għax sewa, jekk ikun Christmas Eve mus nirrispondikom. Alright, imma il-bqija provaw waħdmu, alright, jekk ikolkom bżonn xi ħaġa jduli. Ħallejtkom. Ciao ciao. Narakom. Ciao.
Thank you, sir.